Hello and welcome to part 2 of chapter 9. Here we're going to go over section 9.2, which is our test statistic. So in 9.2 we have a z statistic for one sample problems about the mean. Here we abbreviate this the z-stat. Okay, and our z-stat equation is equal to our x bar minus our mu of 0, which is our the null hypothesis mu sub 0, over the standard error of x bar. This is the test statistic that we use to calculate our z-stat. So it's x bar minus our mu hypothesis over the standard error of x. So an illustrated example of our z statistic. So for our sample, we have a mu 0 for our null hypothesis equaling 170. Remember, that was from our men of the 1970s weight. So we're stating that it equals 170 in the 1970s for men 20 to 29. We're going to take a simple random sample, 64 individuals, so n equals 64, and we know that our standard deviation, our sigma, is 40. So the standard error of the mean is calculated as such. Oh, so standard error of the mean, I don't know why x bar is not in there. So it should be the standard error of the mean is the standard deviation over the square root of n, so 40 over the square root of 64, which equals 5. And that's how we calculate the standard error. Moving our z statistic over, if we found a sample mean of 173, so meaning in 2018 we took men 20 to 29, calculated their weight, and we found that their average weight, their mean, was 173, then we put it into our equation where we have our z-stats equal to the mean of the group we found minus, sorry, some of the graphics aren't popping up, the mu of 0, the mu of the null hypothesis over the standard error of x is equal to 173 minus 170 over 5, which equals 0.60. That is our z-stat, which we will then go to the back of the book, and you can calculate the probability that's associated at 0.6, just like we did with a z-score. Say, though, we found another sample, a different sample of men and from 2029, and we found that their average weight was 185. Then our z-stat would look like this. Our z-stat of our x bar minus mu sub 0, or the mu of the null hypothesis over the standard of x, would be 185. So we're just taking the new mean that we got, plugging it into our equation, minus 170 over 5, and this would give us a z-stat of 3. So here is a sampling distribution of a mean. This is the model, is based on taking all possible samples of n equals 64 from the population with mu equaling 170 and a standard deviation of 40. So here you have one sample at 173, another sample at 185 like we did, and you can keep going, and what you'll see is the normal distribution over time of all the means, all the x bars. So now that's how you calculate a z-stat. So now we go into finding the p-value associated with the z-stat. So a p-value answers the question: what is the probability of the observed a test statistic equal to 1 more extreme than the current statistic, assuming the null is true? So what this is saying is we're trying to determine whether our null hypothesis is whether we can reject the null hypothesis and our alternative hypothesis is more correct, or we failed to reject it. So the p-value is going to tell us how far away we are from our population to what the null is, which is like the status quo, or what is already known. So the way we do this is it corresponds to the ACU, the area under the curve, and the tail of the z-sampling, the distribution beyond the z-stat. So this is what we're going to use table B, or if you have a graphing calculator or a computer software, you can use this to find the area under the curve. Big thing to know with our p-values is the smaller and smaller p-value is, it provides stronger and stronger evidence against our null hypothesis. So here we go. If you were, so this is for our p-value. So remember, we calculated our z-stat from the first one, and we got a z-stat of 0.6. and this was from our sample mean of 173. So if you go back to in your book and you go to table B and you find the z-tenths at 0.6, you'll find that the value associated at 0.60 is 0.7257, right? And remember, anytime you use table B, it's corresponding to that 173 mark and to the left, right? That's this 7257 is this lighter shade of blue on the screen, right? Because that chart is always telling us at that specific point and to the left, the cumulative probability at that point. What we do for the p-value is the complement of it. It's the area to the right? This is the area that we're looking at to see how the complement the other side of it. So in this one, the way we do this, and the way we have been doing this, is to find the p-value, you take 1 minus the cumulative probability that we already solved for, and it will equal 0.2743, which is what the p-value is. So the p-value for here is 0.2743 is the area under the curve, and that's this entire shaded part here. Now, like we said, we want a very small p-value. A p-value of 0.273 is not a small value at all. Normally, we want at least a p-value of less than 0.05. We want a p-value less than that, so we really want to find the area really right here at the end of the tail. This is the area we're really looking for, is that part right there. So let's do the second part. So the p-value for a z-stat, like we calculated, was a 3. This corresponds to the sample mean of the 185 that we did earlier. So that one, if you go to 3, right, or z-stat 3, you go to table B in the back and you find 3, you'll find that the cumulative probability at 3 was equal to 0.9987, which to find the p-value, we find the complement of that part right there, right? So we take 1 minus 0.9987, and that's going to equal 0.0013, which is exactly what we have right here. The p-value is 0.0013 in the right tail, and that's from this part over. And right, so that's a very, very small part, and this is a very small p-value, so this is the one where we would reject the null hypothesis on this one, because this is a very small p-value. Remember, p-value, most of the time we want it less than 0.05. So that's for a one-sided p-value. If we want to go do two-sided p-value, remember two-sided p-value being if we were looking, this was one side, right? We were always looking right here and over to the side. If we have two-sided p-value, it's looking not only at this side, but also this side. So it's the area beyond the tail. The z-statistic for one-sided, two-sided is considered the deviations up and down from the expected, and all you have to do is double the one-sided p-value. So for example, if you have a one-sided p-value of 0.0010, then the two-sided p-value is just 2 times that amount, and you get 0.0020. So if our one-sided p-value was 0.2743 like we had before, and you multiply it times 2, our two-sided p-value is 0.5486, which is drastically higher, and we would for sure fail to reject the null hypothesis. I'm going to stop the video there, and then we're going to pick it up in part 3, going over the significance level in dealing with the p-value.